In the last recording, we looked at applying some of the limit laws. In this recording, we're going to look at some examples that show some of the problems with directly applying the limit laws. For example, with this problem, if we plug 1 directly in the denominator, we will have 1 squared minus 1, which is 0. This function is not defined at x equals 1. So we cannot just directly plug in as the rational theorem allowed us. What we have to do in a case like this is we must take our function, which is x squared plus x minus 2, divided by x squared minus x, and we must simplify it into a form that we can work with. Now on top, when we factor our trinomial, remember that we are looking for two numbers that multiply to be -2 and add to be the positive 1 in the middle. So when we factor the top, we will have x plus 2 times x minus 1, because 2 plus -1 is 1, and 2 times -1 is -2. On the bottom, we have a binomial that has a common factor, so we factor out an x. X times x is x squared, and x times -1 is -x. Then we can simplify this rational by canceling the x minus 1s, and we're left with x plus 2 divided by x. Now the function x squared plus x minus 2 divided by x squared minus x is the same as the function x plus 2 divided by x at every value except 1, because our original function is not defined at 1. But as we're looking at the limit as x approaches 1, we're just looking at what happens as x gets closer and closer to 1, and not necessarily at what happens at x equals 1. So here, the limit as x approaches 1 of x squared plus x minus 2 divided by x squared minus x is going to be the same as the limit as x approaches 1 of x plus 2 divided by x. Since 1 is in the domain of this rational, we can just plug in our 1. So on top we'll have 1 plus 2, and on bottom we'll have 1. 1 plus 2 is 3, divided by 1 is 3. So as x gets closer and closer to 1, our function is going to get closer, y values are going to get closer and closer to 3. Although it will never actually be 3, because it's not defined at 1. Here's a picture. If you look at the picture at the top, here's our function. You'll see there's a hole in the graph at 1, 3. The function at the bottom is x plus 2 divided by x. It is defined at x equals 1. The only difference between the two functions is at that one specific point, 1, 3. It's defined for the function at the bottom, but not for the function at the top. Here's another example of a function where we are evaluating a limit for a value that's undefined. If we plug 0 into this function, we will have 0 squared in the denominator, so this function would be undefined. What we're going to do then is we're going to take this function and we're going to rationalize the numerator. I know in most of the algebra classes you had before, you have rationalized denominators, which means that you have eliminated any square roots that you had in the denominator. Now this time we do not have any square roots in the denominator, but by rationalizing the numerator, we will have a function that we can work with. So what we're going to do is we're going to take this limit, and we're going to look at the function on the top. And we have x squared plus the square root of x squared plus 100 minus 10 on the top of this. And we are going to multiply the top and bottom of this function by the conjugate of the numerator. Now remember, the conjugate means that you take the function square root of x squared plus 100 plus 10, and the only difference is we're going to change that middle sign. And so if we do that to the top, we also have to do that to the bottom. Remember, what we're multiplying by here is called a unit fraction. And with a unit fraction, we are simply multiplying by 1, since the top and bottom of our fraction is the same. So here we're going to have the limit as x approaches 0. Now when we multiply out the top of this fraction, remember that we are falling, and we're going to take the square root of x squared plus 100 times the square root of x squared plus 100. The square roots will cancel, we'll have x squared plus 100. Then we're going to multiply the square root of x squared plus 100 times positive 10. So that's going to be plus positive 10 times the square root of x squared plus 100. And then we're going to multiply negative 10 times the square root of x squared plus 100. And then we're going to multiply negative 10 times positive 10, which is negative 100. And that will give us the numerator of our fraction. On the bottom, we're going to multiply x squared times the conjugate, which is x squared of x squared plus 100 plus 10. Now, at first glance, this does not look like we've simplified very much. However, if you look at the top, you'll notice that a lot of things start to cancel out. For example, we have 100 minus 100, which goes away. We also have 10 times the square root of x squared plus 100 and minus 10 times the square root of x squared plus 100, and those cancel out. And so what we end up with on the top is x squared, and what we end up with on the bottom is x squared times the square root of x squared plus 100 plus 10. And notice you have x squared on top and bottom, and we can cancel those out. That will leave us with the limit as x approaches 0 of 1 on top, and on bottom we have the square root of x squared plus 100 plus 10. Now notice if you plug 0 into this function, it is not undefined. Once we get our function into an equivalent form where we can actually plug in the value, then we just go ahead and plug the value in. So we have 1 on top. On bottom we have the square root of 0 squared plus 100 plus 10. 0 squared plus 100 is 100. So we have the square root of 100 plus 10. The square root of 100 is 10. So we have 1 over 10 plus 10, or 1 over 20. So the limit as x approaches 0 of the square root of x squared plus 100 minus 10 divided by x squared is 1 over 20, which can also be written in decimal form as 0.05. Now these are just some of the examples of issues that you run into when you try to do direct substitution with your limits. The next thing in this section refers to the sandwich theorem. Please go to eLearn and look at the sandwich theorem animation. That will help you to gain a better understanding of the sandwich theorem.